So welcome everyone to our May seminar for the Net Zero seminar series. My name is Grazia Todeschini and I am leading on organizing these seminars. So every month we have an academic from King's, some from outside, giving us a presentation on their research in relation to net zero themes. This month, we are pleased to have Dr. Lander from the Department of Engineering giving us a presentation. Laura Lander is a lecturer at King's Department of Engineering, and her research aims to tackle the challenges of energy storage system and to develop high-performance sustainable battery devices. She applies a multi-scale research approach working at the interface between material science, um, and the design and characterization of energy storage materials and engineering, including life cycle assessment and techno-economics. So today she will be presenting on the development of next generation sustainable and resilient batteries using a multi-scale research approach with the ultimate aim to solve the sustainability and supply chain challenges of lithium-ion batteries. So this is a very relevant topic, I would say, for today's society and for the Net Zero Center. And I really want to thank Laura for her time. So when you are ready, feel free to share the screen and start. I just want to remind that at the end, we will have some time for questions. So if you feel like you can type your questions while Laura is presenting, and I will read at the end, or if you want to wait at the end, there is going to be an opportunity for you to ask your question. So without further ado, now I leave the floor to Laura and look forward to the presentation.
Thank you. Um, okay. Okay. Thank you, Grazia, first of all, for inviting me to the seminar series and also for the kind introduction. So, yes, Grazia said, today I'm going to present my research on a multi-scale approach for the development of sustainable and resilient batteries and discuss a bit more what we're doing in my research group. So, just to start bringing a bit of context to the research. So we all know that our society is heading towards a net zero future, and especially with regards to the decarbonization of the transport sector and the energy sector, we heavily rely on lithium-ion batteries since they allowed, for example, for the development of electric vehicles and also to integrate renewable energies into our grid, such as solar energy and wind energy. So with the current push towards net zero, globally, there's a huge increase in demand for lithium-ion batteries. And for example, here in this graph, I hope you can see my mouse. We can see that we have between 2022 and 2030 an increase of more than 500% with regards to lithium-ion batteries. And for instance, just for EVs alone, from 15 million in 2021 to 145 million in 2030. This, on the other hand, leads to the fact that we also have a huge increase in demand for the materials we need for lithium-ion batteries. So specifically looking at lithium, we can see that again between 2022 and 2030, we have an increase of more than 800% of lithium to manufacture lithium-ion batteries. The problem is now, though, that according to projections, there might be a significant shortfall of lithium for the production of batteries. So we're not even sure if we can produce enough batteries to actually fulfill our net zero strategies. And at the same time, there's another problem, namely more environmentally, of greenhouse gas emissions. And I will come back to this later, but just showing here, again, between 2022 and 2030, we'll have a huge increase in greenhouse gas emissions related to the manufacturing of lithium-ion batteries. So the UK government also recognized the issues we have with our supply chain for lithium-ion batteries and put in place the critical mineral strategy, where they say that it is vital that we make our supply chains more resilient and more diverse to support British industries of the future, deliver on our energy transition and protect our national security. And this is a problem which is not only related to lithium-ion batteries, but to all green technologies. So it can be materials used for wind turbines, for solar panels, for permanent magnets that we use in motors. So it's really an issue that that encompasses all clean energy technologies and that we have to tackle in the future. So again, besides our supply chain issues, there are also the environmental issues. And when you open newspapers, there are a lot of articles on the environmental problems that we have with electric vehicles. So it's not all green as it seems, but there's a lot of discussions and very polarized discussions also on the environmental impacts of our electric vehicles and the batteries specifically. And whilst I do not necessarily always agree with those articles just because they don't have a lot of scientific rigor, I have to admit that there are indeed some issues with lithium-ion batteries with regards to sustainability. And if we look at the value chain and the life cycle of lithium-ion batteries, looking from mining activities, raw material processing and refining, then the production of the materials of lithium-ion batteries, the use phase and also the recycling reuse, we can see that along the value chain there are different environmental issues. So for instance, looking at the mining activities, we have issues with habitat destruction, resource depletion. Mining also requires a lot of energy and produces a lot of waste streams, which are often toxic, for instance. Then when we look at the manufacturing of materials for batteries, we again produce a lot of wastewater. Often those manufacturing procedures require a lot of high temperature, so again, a lot of energy consumption. For battery and cell manufacturing, you need very specific conditions, in this case, dry rooms, again, which are very energy intense. And also, of course, when we recycle our batteries, we often use harsh chemicals and again, produce a lot of waste. So as we can see along the life cycle of batteries, there are indeed a lot of sustainability issues, which again, we also need to tackle in addition to the supply chain issues we have. So we can see that indeed we need an overhaul of our current battery roadmap, which heavily relies on lithium-ion batteries, and we really need to develop batteries which are more resilient, more sustainable, and allow us to diversify a little bit our battery portfolio. So this brings me to the main bulk of my talk. So I will start first explaining a little bit the basics of batteries and then explain in more detail what we're doing in my group. So one topic will be on the development of more advanced battery systems, specifically aluminum-ion batteries. Then I will talk a bit more about recycling and then show some pictures of our lab facilities and our capacities. So lithium-ion batteries and their basics. So I will start with lithium-ion batteries because they're kind of the status quo and an easy system to explain how batteries actually work. So in lithium-ion batteries, we have about 5 main components. So we have our cathode material, which is often transition metal oxide, in which lithium is incorporated. We have a liquid electrolyte. We have a separator between the cathode and the anode. And on the anode side, we often have a graphite-based material. So what happens on charge and discharge in this battery? So when we charge our lithium-ion battery, the lithium, which is within the cathode, is extracted and diffuses through the separator and through the liquid electrolyte and intercalates into the anode material, into the graphite. At the same time, we have electrons which migrate through an external circuit and load our battery in that sense. On discharge, so for example, when we use our battery to power our phone, our laptop, or our electric vehicle, what happens is the reverse process. So our lithium deintercalates from our anode material, from the graphite, migrates back to the cathode and intercalates there. And at the same time, our electrons again move through an external circuit and power our device. And so this is kind of the reversible process. And what is important about lithium-ion batteries compared to other battery systems, for instance, is that this process is reversible. So we can charge and discharge our batteries compared to, for example, other alkali batteries, which you have to throw away once you discharge them completely. So I showed you on the cathode material that there are often lithium transition metal oxides. But actually, there's a large variety of materials that you can use for cathodes, and this is one of the main research topics within the community of lithium-ion batteries. And the cathode material is so important because it really allows us to tune our properties of the battery. So what we want with a lithium-ion battery, if, for example, we think about electric vehicles, we want to have a large range. So we want a high energy density practically of our battery. And we want safety, we want cost efficiency, and all these kind of things that we need in our everyday life for our electric vehicle. So anyway, in the past decades, as I said, there was a lot of research going on the cathode material side, and I just want to show you a few of the materials that have been researched. So 3 of the main materials that are currently used are the, as I said, the lithium transition metal oxides. They are often called also layered oxides because they have this kind of layered structure, where you can see the kind of transition metal oxide polyhedra connected in those layered structures, and then in between you have the lithium, which then diffuses and intercalates and is extracted, as I showed you in the previous slide, depending if you charge or discharge. You also have these kind of spinel structures, also lithium transition metal oxides. Those are materials that are a bit older already, so they were used, for example, in the first Nissan Leaf electric vehicles, but they're not so much used anymore nowadays, just because in terms of their performance, they're not as attractive anymore. And then we have the lithium metal phosphates, which are becoming more and more popular, specifically the lithium iron phosphate. And so, for instance, previously they were mostly used on the Chinese market for electric vehicles and electric buses, and only in recent, like in the recent 1 or 2 years, are coming more and more also into the Western market. Specifically, Tesla, for example, one of its latest models uses lithium iron phosphate materials instead of what they used previously. And then there's a variety of other materials. There are silicates, borates, vanadium-based materials, and so on and so forth. And all with different properties and different structures, and yeah. But again, those 3 classes are the most commonly used. And as I said, so with the material, the cathode material, you can really tune your battery properties. And so just looking here at the parameters, performance parameters of safety, energy density, cycle lifespan, and cost, for instance, we can see that there are vast differences. So for instance, for example, lithium cobalt oxides, which we often use in our cell phones, or those other layered materials such as NCA, which was used in previous Tesla models, on NMC materials, which are used practically in all other electric vehicles, are relatively unsafe in that sense, where, for instance, on the other hand, lithium iron phosphate has a very high safety performance. And this is also one of the reasons why, for example, lithium iron phosphate is coming more and more into the market. Similarly with cost, for instance, so layered materials such as NCA, NMCs are very cost intense. Again, lithium iron phosphate is relatively cheap. And also we can see in terms of cycle lifespan, again, LFP is much better than, for instance, NMCs, which we are using in BMWs and Volkswagen electric vehicles. On the other side, if we look at energy density, or if we translate it into an electric vehicle performance, this would be the driving range. Lithium iron phosphate is not quite as performant as, for instance, NMC and NCS, which are really at the forefront in terms of energy density. And this kind of table also shows quite nicely that we often have a trade-off in terms of properties. So we have safety, we have cost, we have performance, and depending on your application and also depending on what the market really wants, you have to choose your materials, but also you have to accept certain trade-offs, be it with safety, be it with cost, and so on. So after covering some of the battery basics for lithium-ion batteries, I now want to go into more detail of aluminum-ion batteries and what we actually research in our lab right now. So I showed you the supply chain issues we have currently with lithium-ion batteries with regards to raw materials demand, specifically with lithium. And so there's a lot of research going on currently in terms of finding alternative battery systems. So one of the strongest contenders right now, sodium-ion batteries, for instance. However, sodium-ion batteries are not as performant as lithium-ion batteries, specifically with regards to energy density. So often sodium-ion batteries are used either in smaller applications such as electric bikes, maybe in very small electric vehicles which you use in city centers, for example, where you don't need a lot of range. But yeah, you're quite limited with this kind of battery system, and it will not be, a real replacement for lithium-ion batteries in the future. So looking at the periodic table of elements, one of the materials which is very interesting in terms of electrochemical performance and promising performance for batteries is aluminium. So aluminium, first of all, has the advantage that it's much more abundant compared to lithium in the Earth's crust. So having this kind of problem of supply chain issue that would be solved. Also, aluminium is much more distributed, and we don't have these kind of materials monopolies that we have currently with our lithium supply chain. In terms of cost, aluminium is much cheaper than lithium. Also, we have less price volatilities, again, which is related to supply chain bottlenecks, for instance, with lithium, which led to a lot of market and price fluctuations in the past. And with regards to energy per volume ratio, which is much more favorable for aluminium compared to lithium, we would be able to make our aluminium-ion batteries much smaller, up to 4 times smaller than current lithium-ion batteries. And this means that, for example, in electric vehicles where we are size limited, we would be able to get much more energy in a much smaller volume than compared to lithium-ion batteries, which is a huge advantage. With regards to the energy density, aluminium-ion batteries would have a small disadvantage. However, they're still kind of comparable and not as, the difference is not as big, for example, as between lithium and sodium-ion batteries. So the setup of aluminium-ion batteries is pretty similar to lithium-ion batteries. So again, we have our cathode material, which is an inorganic transition metal oxide or chalcogenide. We have our separate, we have our anode. The anode in this case is aluminum metal. It's not graphite, which is also one of the big advantages of aluminium-ion batteries, since we could get a lot more energy density from this. And we have a liquid electrolyte. So whilst the functioning of aluminium-ion batteries has been proven already in literature in the past, there's still a lot of key challenges. So one of the biggest differences between aluminium-ion batteries and lithium-ion batteries is that instead of lithium, we cycle aluminium, so aluminium 3+. But since aluminium 3+ has a very high charge density, so meaning charge of 3 on a small radius, it has a lot of strong electrostatic interactions with our inorganic cathode materials, so for example, the oxygen or the transition metal oxygen framework. And this leads to the fact that we can't really extract and intercalate our aluminium because it gets stuck within the material. And this often leads either that we have short battery lifetimes, because our material, for example, just decomposes when we put too much pressure and try to extract our aluminium, or we can't really achieve the theoretical energy densities because we can't really intercalate aluminium. So there are a lot of different difficulties replacing lithium with aluminium in terms of cycling performance. The other big issue is that there is a lot of uncertainty about the reaction mechanisms. So as I said, aluminium-ion batteries are still a very new technology. And in terms of reaction mechanisms, so meaning what is actually going on in the battery on a fundamental molecular level, is still not quite known. And in the literature, there's a lot of different opinions on, for example, do we intercalate actually aluminum 3+, or it was also observed that we intercalate more those tetrachloroaluminate molecules, which is a completely different mechanism and which we actually do not want to pursue. So again, there's a lot of uncertainty, and this also means that we have no real control of our battery functioning. Another issue is also, and this is more related to the fact that it's quite a new system, so there haven't been a lot of whole system studies, meaning the environmental and economic impacts and benefits haven't really been assessed for this battery system, and we don't really know yet where the hotspots that we need to tackle and where we have to be careful in terms of materials development, for instance. So what we do in my group, so we have Fiona Simpson, who's a PhD student and who's really doing great work on aluminum-ion batteries, trying to understand the fundamental reaction mechanisms that are happening within the battery, and also trying to optimize their performance. So her focus is on the development of transition metal sulfides and selenites. And why do we focus on this kind of class of materials is because, as I said, we have a very high charge density with aluminium 3+, and very high electrostatic interactions with oxygen, for example. So if we replace oxygen in the cathode material with sulfides or selenites, we have a much softer anions in that sense, which would reduce the electrostatic interactions with aluminium 3+, and which allow us to more easily intercalate and extract aluminum from our cathode material. So in terms of performance, this would be already a huge step up. We will do, or we use a lot of inoperandi and ex situ characterization techniques, such as inoperandi X-ray diffraction or X-ray absorption spectroscopy, to really understand, for example, how do our materials evolve upon charge and discharge, so when we extract aluminium 3+ and intercalate it, and also trying to understand in the sense where our performance bottlenecks, so how do our materials change, how do our materials degrade, where are the issues that we need to tackle, and how can we improve our materials, specifically the cathode material, in order to overcome those bottlenecks and to optimize the performance in that sense. So this brings me to the next topic of battery recycling, which we're also looking at in our lab. So again, the aluminum-ion battery was more on the very fundamental scale, on the atomistic scale. Recycling we will be moving more to a macro scale approach. So hence the multi-scale approach of our research. And so the issue with recycling right now is that, as I showed you in the beginning, we have a huge increase in demand of lithium-ion batteries. But this, in the end, will also mean that we will have a lot of lithium-ion battery waste in the coming decades that we need to take care of. And at the same time, I also showed you that we have, with this lithium-ion battery demand increase, an increasing demand for the raw materials. So I showed you the issues with lithium, but also, for example, specifically with nickel, we have here an increase in demand of up to a factor of 24. Cobalt is doubling until 2030, sorry, and also manganese, we have a huge increase in demand. So we will need to make sure that actually, to be able to fulfill our demand, that we have enough materials that we can provide for the manufacturing. And here, end-of-life batteries are really a very valuable source of raw materials, since recycling would allow us to extract lithium, cobalt, nickel from end-of-life lithium-ion batteries and reinsert them into the battery manufacturing cycle and kind of close the life cycle of those batteries. So whilst recycling of batteries is very important, it's also very difficult because, as I showed you in one of the first slides when I showed you how batteries are set up, we have a lot of components in there. We have the cathode, we have the anode, we have the separator, we have the electrolyte. They're all different chemical compositions. So it's all very complex in terms of separating it. And also, battery recycling is something that has not been researched in a very long time because nobody really thought about the end of life of batteries. First of all, we focused on actually developing those batteries and making them high performance. So in the past few years, there's been a much stronger push towards developing efficient recycling methods. And to date, there are 3 recycling methods that have really come out of this kind of research. So the mostly used ones are the pyrometallurgical and hydrometallurgical ones. And there's also a newer recycling method, which is called direct recycling. And just to kind of explain very high level what's happening in those recycling pathways. So the hydrometallurgical one practically uses a lot of leaching processes and chemical separation processes to decompose specifically also the cathode material and to separate all our transition metals and lithium out of the battery. The pyrometallurgical process uses as a first step very high temperatures to kind of melt most of the components down, where we form on one side kind of a slag, which contains some of the metals such as copper, aluminium, manganese, and also we have and also lithium actually, and we have the formation of this kind of mixed alloy, which is then further treated via hydrometallurgical processes similar to the ones we saw here to extract cobalt, nickel, and manganese out of it. The direct recycling one is more straightforward. It means that we don't destruct our chemical composition of our materials within the battery, but actually try to retain it as much as possible and just to refresh it. So for instance, looking at the cathode material, we would just separate the cathode from the rest of the battery, do some chemical treatments to kind of rejuvenate it and put some more lithium in it, maybe which was lost during the previous cycling procedures, and then put it back into a new battery. And this is actually one of the processes which is kind of hailed as the most sustainable one and the most efficient one. Recycling becomes also more and more important in the past years since the EU launched its new battery directive, and I think 2023 it started to be enforced. And so the EU battery directive tackles a lot of the sustainability and supply chain issues that I discussed in the beginning. And so one of the main points are, for instance, that manufacturers have to declare the carbon footprint of batteries. We also have the establishment of the battery passport, which contains a lot of information in terms of the materials that are used, the cycling, the usage, and also again the carbon footprint. And recycling is one of the main points of the battery directive, namely that starting from 2031, each newly manufactured battery that is put on the EU market needs to have a minimum recycled content within the battery. So meaning that within our lithium-ion battery, when we produce it, we need to incorporate 6% of recycled lithium, 6% of recycled nickel, and 16% of recycled cobalt. The issues now with those restrictions and with those minimum recycled content limits, that looking again at the significant increase in cathode demand, and specifically also looking at the various transition metals such as cobalt, nickel, and also looking at lithium, we need to make sure that we actually have enough recycled material to fulfill this demand. The problem is now that batteries can last up to 15 years. And so meaning there's a huge gap between when we put our batteries on the market and when we will be able to recycle them. And 15 years is probably one of the best case scenarios, meaning this is when the battery will die the quickest. And so the question is now really, will we even have enough end-of-life batteries available for recycling to fulfill the growing demand for recycled material to produce new batteries? And what will be the cost impacts of potential supply chain bottlenecks for recycled material? And here we're wondering if recycled battery material will become the new critical material, which have been so far only lithium, cobalt, nickel, and of course virgin material. But now, given with this new EU battery directive, there might be really a change and a shift in the market and in the supply chain bottlenecks of those recycled materials. And so I don't want to talk too much about it because this work is done by one of my PhD students, Marlene, who will be also presenting at the Net Zero Center PhD seminar series on the 13th of June. So if you want to have more, or if you want to know the answers to those questions, I encourage you to join the seminar. And so, yeah, just to finish up the talk, to give you a little bit of explanations of what we're doing in our lab and what our capacities are. So we have a new battery lab in the Quad here on the Strand campus. And so our focus, actually, again, we have a multi-scale focus on the development of battery materials. So on one side, we have the facilities to synthesize new battery materials. So we do solid-state synthesis, we do solvable thermal synthesis. We have a lot of battery testing facilities where we test batteries from very small scale, so from coin cells, more fundamental testing, also up to bigger small packs. So for instance, my colleague, Dr. Francesco Ostuccia, who's also working on batteries, has more large-scale battery testing facilities. We do fundamental materials characterization from X-ray diffraction to electron microscopy and chemical composition analysis. And also, as I mentioned, we look at recycling processes for lithium and sodium-ion batteries from an experimental point of view, but also looking at the techno-economics and the supply chain. And also, we're looking at sustainability assessment using life cycle assessment methods. And yeah, with this, I would like to thank you very much for your attention, and I'm looking forward to the discussion.
Thank you very much for the presentation. So now we start formally the discussion. So I see that there is already a question in the chat, actually now two. So if either Catherine or Pete are happy to talk, yeah, they can ask their questions. If not, I'm happy to read it. So maybe we just wait a second and then if
yes, I'm
perfect.
Hello, thank you very much for a very interesting and well put together talk. I just wondered about aluminium, as you were indicating it was proving to offer great hope in the recycling, but my understanding is that it's a real fire hazard. I know the Navy have had a history of problems with using aluminium on their ships, and it caused terrible burns to servicemen and women. And I just wonder how you're dealing with that if you're looking at it seriously as a recycling option. Thank you.
Yeah, thank you very much for the question. So actually what is quite interesting that in the battery community, aluminium is held as a much safer option. Specifically, for instance, when we use it in batteries, when you use lithium metal, you often have the risk of so-called dendrite formation, so where we have elemental lithium which is growing within the batteries and causing short circuits, and then you have those battery fires which you sometimes see in the news. Aluminium in this sense is much safer, that this is practically not happening, and you don't have these kind of battery fires, or at least they haven't been observed to date, than you have with lithium. And also in the sense of how we used aluminium, for example, in the lab so far, and also on a bit larger scale, there weren't really any reports in that sense that in the battery context or in the aluminium recycling context, there were a lot of safety issues with that. But thank you very much for mentioning it, and I think I will definitely look more into this and to see how these kind of risks need to be taken into account for aluminium-ion batteries as well in the future.
Thank you. Thank you very much.
Thank you for the question. Now there is a second question from Pete. Not sure if Pete is able to come. Yeah.
Yeah. Thank you very much. Thank you, Laura, for that very stimulating talk. There's a huge increase now in battery energy storage. This is being driven by the, unreliable, unpredictable, renewable energy. You've got to store this energy somewhere. So the demand is probably much bigger than you showed in your slides, which were developed about 4 or 5 years ago. Mm-hmm. So my question is there going to be enough capacity, lithium even, for coping with this large increase. And I'm also concerned about the longevity, the lifetime of the batteries, because I believe that under the conditions they'll be used in BESS, they probably only have a lifetime of 8 to 10 years and not the 15 that you were quoting. Could you comment on that, please?
Yeah, absolutely. Thank you very much for this very interesting question. So I fully agree. So there won't be probably enough lithium or enough batteries to actually cope with the demand. Specifically, I mean, I showed a lot on the electric vehicle side, but as you said, also battery energy storage, like on larger scale, is a real issue. And here again, this is where sodium-ion batteries, for instance, play a big role, because whilst they don't have a very large energy density and are not very useful for electric vehicles, there's big hope in terms of large-scale grid storage, because you don't have the same space limitations, for instance, that you have in the car. So you can have very large battery installations using sodium-ion batteries, and you can replace practically part of the demand of lithium-ion batteries. So yeah, as I said, sodium-ion batteries with regards to BESS is really the hope to alleviate some of the pressures we have on lithium-ion batteries. In terms of lifetime, I think it really depends how you use your battery. And I think there's a lot of contradicting information within the scientific community, at least, depending on how you test your battery. So often it's also on lab scale, it's not necessarily on large scale. So they often try to simulate the conditions you would use it in a large scale context, either in electric vehicles or in grid storage, and trying to understand how the degradation is and how long a battery would live. But of course, if you would do this in a one-to-one scenario, you would need to test your batteries for 10 years. So there's a lot of, again, uncertainty and predictions and projections going on. What I usually read is that specifically for electric vehicles, the lifetime was actually underestimated. And whilst many people thought, okay, even under rough driving conditions and cycling conditions, a battery would last maybe only eight years. Actually, we see already batteries lasting, and those are some of the early battery systems, so not even the the more sophisticated ones that we put on market now, lasting up to 12 years, for instance. And so again, I believe also with grid storage, so larger scale battery energy storage systems, it really depends how we use them, also what kind of material we use there. So again, I showed in the battery basics section that, for example, lithium iron phosphate has a much longer lifetime than NMC materials and NCA materials, which we use in cars. So using LFP, for example, in grid storage would also allow us to use our batteries much longer. But yeah, again, it really depends also on the environmental conditions, how you cycle your batteries. So I think there's still a lot of uncertainties how this will actually turn out.
Thank you.
Thank you. I also
see a follow-up question from Pete, and then there is a raised hand, but maybe we can look at this question before we move to Wei.
Yeah, thank you for that answer. It's very comprehensive. I've been studying the explosions in large energy storage systems, and it strikes me that there will always be a risk of vapor cloud explosions from whatever metal you use in the battery, as long as you have an organic liquid electrolyte. So my question is, does aluminium require the same kind of organic electrolytes that sodium and lithium are using? Or can you use an aqueous solution or a solid state electrolyte?
That's a very interesting question. And also, if you're interested in the kind of safety aspects, as I said, my colleague, Dr. Francesco Stuccia, he does a lot of safety of lithium-ion batteries, so it might be worth contacting if you haven't done so yet. But yes, so aluminum-ion batteries use different kind of electrolytes. So as you mentioned, lithium and sodium-ion batteries have those organic electrolytes, which at certain temperatures then kind of form these flammable vapors. Aluminum-ion batteries use ionic liquids, which are much more stable, also at higher temperatures. And for instance, there were also studies for ionic liquid electrolytes used in lithium-ion batteries that have shown that they're even sometimes fire suppressing. So in this sense, there's a lot of safety advantages for aluminium-ion batteries. You can also use aqueous electrolytes. The battery system is though quite different, and you are limited with regards to your energy density. But there's also a lot of research going on aqueous aluminium-ion batteries.
Thank you. Thank you. That would be a real selling point, I think, for aluminium.
Yeah, absolutely. Absolutely. Thank you.
Thank you for the interesting discussion. So now we have a hand raised by our colleague Wei. So Wei, if you're ready, please ask your question.
Hi, Laura. Thank you for the talk. So I have a question about you mentioned your PhD student will talk about supply chain, but I wonder, like, recycling battery, what's the kind of the current, cost? Is that more expensive or cheaper than using the, I would say, the raw from the original mining process? I mean, what's the kind of cost ratio between the two different ways to get lithium or whatever, material?
Yeah, that's a really important question right now. So the problem is that currently recycling is not really profitable for the recycling industry, and this is also why there's not really a very large recycling industry, for example, in the UK specifically, or also in Europe, because we don't have a lot of end-of-life batteries that we can recycle at this point. The recycling processes are not very developed and not very efficient at this point. And you have a lot of investment in terms of labor, electricity, all sorts of other things that you need to recycle your batteries. So actually, right now, depending on how you recycle your batteries and also where you recycle your batteries, you can actually often make a loss on the battery recycling process. So I did a study on this like a few years ago, actually, where I compared battery recycling in countries such as UK, Europe, China and South Korea or something. And we could see that when we recycle, for example, in the UK versus recycling in China, we make losses, whereas in China they make profits, just because, the cost structure is like labor costs and electricity costs are much cheaper. So yeah, right now I think it's more profitable actually to use raw materials and not to recycle, unfortunately.
Okay.
But hopefully this will change in the future.
Yeah, I think they are probably also without, in addition to the technology development. So you mentioned about the EU policy, kind of driven initiative. Do you think there are any other, other policies, like other mechanism to ensure they can meet that policy, like I can't remember the policy you mentioned about, to make sure at a minimum material, recycle at a certain time point.
Yeah, that's something we're currently looking into and discussing also a lot with industry representatives on, for example, battery manufacturers, but also electric vehicle manufacturers, to try to understand, and also policy representatives to try to understand what those mechanisms would be. But for now, I have to say the outlook is not very positive, and people are not really sure how this policy would actually be met and if it's possible. And again, there might be a scenario where actually we will import the recycled material from other countries which have much better recycling processes and efficiency. So for example, again, China is in terms of recycling much more advanced. And and in order to fulfill this policy that we bring recycled material from outside, it's not necessarily, I assume, what this battery directive wanted to achieve, because I guess they wanted to achieve that we have a more UK, Europe-based internal supply chain. But as it seems now, the directive and the legislation is not very realistic, so we need to find other ways of fulfilling it.
Thank you very much.
Thank you for this good discussion. Now we have another hand raised by Dawn. So when you're ready.
Thanks, Laura. That was really, really interesting. Actually, that same conversation you're having about recycled material in batteries is very similar to the plastics industry at the moment as well, isn't it, with their recycled content? But my question was possibly slightly tangential to your talk, but it was about the mining of aluminium or any of the raw materials and how we could possibly go about giving them any sort of signatures so that we know the provenance of those materials, because where the aluminium or the lithium comes from has a big effect on, you know, how it's mined and the human rights of the countries, or if it's from the Amazon, the deforestation. So do you know of any research that sort of gives any sort of signature to that material?
Yeah, that's also a really important topic, I think, in the whole policy area of batteries. So specifically with this battery passport they want to introduce, I think they also in this battery passport want to include more information on the provenance of those materials, and to make sure they come from areas which have, for example, more worker protection. So, you know, like I missed the word, like yeah, safety for workers and working conditions. Also in terms of sustainability issues, waste treatment, and these kind of things. There are also, I know some companies who are trying to kind of advise battery manufacturers more on the provenance of battery materials and how to ensure that they can be met. But to be honest, sometimes I'm a bit not suspicious, but I'm not quite sure if this can be actually controlled in such a rigorous manner, because of course there are always ways of, you know, not doing your due diligence. And I think we saw this maybe in the textile industry, where people also, you know, were looking more at the provenance, and actually certificates were not really followed up on, or were not really truthful. So I think they're trying to put in the legislation in place. How it will be, again, implemented and, you know, followed through, this I'm not so sure.
Thank you.
Thank you for this question. So I don't see any other hand raise or question in the chat. So I know, Laura, we have been asking you a lot of questions. So I will just ask you a very general question, more perhaps looking at the future. I was wondering if maybe this type of challenges and you know, cost and all the things that really we discussed may lead to developing alternative storage solution, not batteries necessarily, perhaps hydrogen or other technologies. So I was wondering if you maybe have any comments on this and how you see maybe the landscape developing maybe in the next few years.
Yeah, absolutely. So I think there's always the competition, batteries versus hydrogen. In my opinion, I think it will be a combination of technologies, and I think this is also the most important, because it allows us, first of all, to have more independence and not be so reliant on just one technology. And also each technology has its own advantages and disadvantages, and there's no one fit for all. I think it's really important, and this is a mistake we've done with lithium-ion batteries, just assuming that we need to use one technology for all applications. And in some cases it's, I don't know, possible or unnecessary. So for example, lithium-ion batteries in many applications are completely overperforming and wouldn't even be necessary. And so yeah, so here I think the difficulties we see and the challenges with lithium-ion batteries will indeed encourage people to look at other technologies. We have hydrogen, we have geothermal, pumped hydro in different contexts and scenarios, of course. And yeah, so I think there will be a diversification of our technology portfolio, definitely.
Yeah. So this reminds me of a conversation we have also on the power system area where, we think diversifying a bit generation technologies, maybe not relying always on wind or on solar, but a mix, it's probably the best solution moving forward. So probably it's a similar, I guess, idea for energy storage.
Absolutely.
Yeah. So I think some people are leaving because they're going to the next meeting, I believe, and I think we ask you a lot of questions. So I would like to close the webinar here, and thank you also for anticipating that the next seminar will be on June 13th with our PhD students, but that will be in person, and details will be circulated shortly. So I really thank you for your talk and for the attendees for the very interesting questions and discussion. And I look forward to see everyone at the next event. Thank you so much.
Thank you so much again, also for the questions. Thank you.
Thank you.